Okay, gentlemen, let's continue. So we'll talk about inverse transforms and transforms of derivatives. So we will talk about the second part, transforms of derivatives. Now we are going to see two examples related to transforms of derivatives. Okay. So now let's immediately apply what we have just learned to this differential equation. That is first order differential equation, right? It is linear as you see because all the coefficients are, what is it, constants. Here we have y prime plus 3y is equal to 12 times sine of 2t. And also here initial value is given at 0, the value of the function is 6. That means that the graph of the function is passing through this point. Why is something, maybe it is, so we are looking for this solution, something like that. We don't know yet. Okay, now the first thing we have to do here is actually, of course, in a different way we can solve this, but here our purpose is to apply what we have just learned into this equation. And now in the near future you will see that there are a lot of problems we cannot solve them using the methods that we have learned so far, but using this Laplace transform it is much easier, okay, and more practical, and also actually, how to say, labor saving job. So here if I just take the Laplace transform on both sides and also just keeping in mind the linearity property of this transform, what we have here. Here we have Laplace transform of the first thing, this one is y prime. Here we have our independent variables t. So here y prime of t. Plus, how about here? There's a constant. I can just keep this outside. And here we have Laplace transform of y. On the right hand side, I have 12 times Laplace transform of, what is it? Sine of 2t. Right? Now we have just obtained the formula for y prime of t, right? And this thing, what is it? That is equal to starting with s because the order is 1 here. So that thing is equal to s times capital F of s, right? And minus 1 less than 1 is equal to 0. So here we have f of 0 plus 3 times. Okay, since here it is y, let me just use also y. Okay, and 3 here. What is the Laplace transform of this y? Also, it should be y of t. Also here it is capital Y of t. Okay, that's equal to 12 times. And we know how to evaluate the Laplace transform of sine of 2t. Right here we have 2 squared. That is 4 over s squared plus 4. Not 2 squared, it's just k, right? It is 2. K over s squared plus k squared. Maybe this k here. Okay. Now, is it transform? Okay. As you see here, it has just become an algebraic equation in capital Y of s, right? Capital Y of s, everything else take them to the right hand side. Now I can find the capital Y in terms of s, right? And what is f of 0? F of 0 is equal to 6, right? So here, these two things, capital Y is a common factor. So here we have capital Y of s times, here we have s plus here we have 3 is equal to, take it to the right hand side, 12 times 2 is 24. Okay, here we have 24 over s squared plus 4, right? And here we have plus 6, or which is equal to, I can simplify this. Or now if I divide both sides by s plus 3, what do we get here? Y of s is equal to 24 over, here we have s plus 3 and s squared plus 4 plus, here we have 6 over s plus 3, right? Or I can just simplify this. Here we have s plus 3, s squared plus 4. If you multiply by s squared plus 4, right, the common denominator. So here I have 6s squared. 6 times 4, it is 24, and plus 24, that's equal to 48. Did I forget anything? Here we have ys 3, right, s plus 3, right, here we have 3, and 12 times, okay, everything's all right. So now, if I just apply inverse Laplace transform to both sides, right, I will get this y function. Okay, to do this one first, I have to decompose this fraction. That is elementary thing, but still it takes time. Now to do this one, here we have 6s squared plus 50. Why this 48 here? Let me here 6 times 3, 6 times 4, 24, and 12 times 2, it is 24, right? So we divide by s plus 3. Okay. Okay. Did I make a mistake somewhere? Okay. Guys, there's a small mistake here. This should be 13. Actually, it doesn't matter, but the question is 13. And also this should be 13. This should be 13. At the time, this will be 26, right? That is 26. And 24, here we will have 50. I will correct this later. Okay. Just give me 3 seconds. Okay. Continue. No problem. So here it is 13. I'll correct this later. What is 13? Here we will have 50. Okay. So in the next step, we have to decompose the fraction. And also, you know how to do this. That's why I just typed this earlier, not to waste time. So this y of s equals 6s squared plus 50 over s plus 3 times s squared plus 4. So in the denominator, we have a factor that cannot be factorized, and also degree is 2. How can I write this? We can write this as a over s plus 3 plus bs o plus 3, c over s squared plus 4. Okay, why? The reason is when you bring it to a common denominator, and also we need to have here a quadratic expression. All right, if you just write here c, here we have linear expression and quadratic, and we will not be able to determine this a. All right, then bring it to the common denominator, right? So a times s squared plus 4 plus bs plus c times s plus 3, right? And also by substituting some suitable values for s, we can determine the values of a, b, and c. For example, if s equals -3, this part will disappear, right? If equals -3, here we have 9 times 6 plus 50. That's equal to 9 plus 4, 13. And that is, this thing is divided by 13. It gives us 8. And how about C, for example? If S equals 0, this B will disappear. I know the value of A, right? And substitute 0 for S. On the left-hand side, we have 50. And evaluate this, I can get the value of C. That's equal to 6. And how about to determine this B? Substitute any suitable value, because I know the value of A, I know the value of C, right? Since this is an identity, for every value of S, left-hand side should be equal to right-hand side. So suitable means easy to evaluate. What is it? Let's say it is 1. If you substitute 1, and we can get the value of B. That's equal to -2. So now if I substitute these values into this equation, what I have here, 8 over this plus minus 2s plus 6 over s squared plus 4. So we have this thing, right? So 6s squared plus 50 over s plus 3 times s squared plus 4 can be decomposed as this thing, okay? So as you see here, now we are familiar with these fractions, right? Algebraic fractions. Actually, I can also split this, right? And also I can write it as this thing is minus 2, take this out. So minus 2 is out. Here we have 8, also keep this out. Here we have 1 over s plus 3, 1 over s plus 3, right? And minus 2 times, here we have minus 2, take this out. Here we have s over s squared plus 4. And the third thing is 6 over this fraction, that is, also take this 3 out, 2 over s squared plus 4. Here we are just writing everything in the form that we have already obtained, right? And we know what functional Laplace transform equals 1 over s plus 3. What is it? E to the power minus 3t. So here we have 8 times e to the power minus 3t, right? And here we have minus 2 times cosine of 2t, because here we have s, here we have 2 squared. And here we have 3 times, what is it? Sine of 2t, okay? And we are just getting the inverse of this y because we have already obtained this y, and it gives us our original function. So the solution of the given initial value problem is this thing, okay? That is the main idea of applying Laplace transform or its inverse into the differential equations with constant coefficients. Let's say another example. So the first example was the first order, the second one is the second order. Now you got the idea, we'll go a little bit faster, okay? So we need to solve this second order linear differential equation with constant coefficients. As you see here, all the coefficients here is 1, here it is negative 3 and plus 2, right? It is e to the power minus 40. Okay, so first step is what we have to do here. These are the initial conditions. I need to take the Laplace transform of both sides, right? So what I get here, if you just take the Laplace transform both sides, just put here this L, right? And here we have L, and we know how to evaluate these things by using the theorem, and here and also by using the linearity property of Laplace transform. I can just write it in this form, Laplace transform of y double prime minus 3 constant, keep it out. So L of y prime plus 2 times Ly equals Laplace transform of e to the power minus 40. Now what we got here? We know what it is. That's equal to s squared and y of s, that is Laplace transform of y, minus s times y of 0 minus y prime of 0. As you see here I'm using two given initial conditions here. The second one, minus 3 times, how about this one? That is s times capital Y of s minus the value of the function at 0. Also it is given here, plus 2 times y of s. On the right hand side, what is the Laplace transform of e to the power minus 40? That's equal to 1 over s plus 4, right? So now, just we need to simplify. That is simple algebra, right? We remove the brackets, and after that, this y of s, keep them on the left-hand side, and the rest take them to the right-hand side, and do some simplification. What we got here? Here we have this y of s here, right? Here we have another y of s. Here I have y of s. If you just take this out, from here I have s squared, right? From here I have minus 3 times s, minus 3 times s, and from here we have 2. And the rest take to the right hand side. What is y of 0 is equal to 1. So here we have minus s. Take to the right hand side, here we have s, right? Y prime of 0 is equal to 5, right? And also here we have 5. Minus 3 times minus 5 is 15, right? And 15. Okay, y, no. Here we have y of 0 is equal to 1. Minus 3 times minus 1, it is 3, right? And here we have minus 5. So that is minus 2. Right? Minus 5 plus 3, that's equal to minus 2. And take to the right hand side, here we have 2. And on the right hand side, we have 1 over s plus 4 here. So now I'm trying to make this capital Y the subject of this formula, right? So I'm trying to just isolate this and keep it on the left hand side, everything else to the right hand side. What we have here then? Here I have y of s plus 2 over that expression plus 1 over this. And it's just a quadratic expression. We know how to factorize it, right? And we see here all the factors in the denominator, they are linear functions, right? Or linear factors. Then, by just doing some algebraic manipulation, here we have s minus 1 times s minus 2 plus s plus 4, right? What is missing here? I should multiply this by s plus 4, s plus 2 times s plus 4 plus 1, and simplify this. We get s squared plus 6s plus 9. If all the factors in the denominator are linear, how can I write this? It is just equal to a over the first factor plus b over the second factor plus c over the third factor, right? And doing the similar thing, I can determine capital A, capital B, capital C, bring into the common denominator, since we are claiming that this is an identity, right? And this numerator should be equal to the numerator of the right-hand side. Now, if s equals, for example, 1, right? This will disappear, this will disappear. I can get the value of a as equal to minus 16 over 5. And how about if s equals, here we have to make this disappear, s should be equal to 2, right? This equal to 0, this equal to 0. I can determine the value of b as equal to 25 over 6. And how about if s equals negative 4? This will disappear, right? And also this will disappear. From here, I can determine that b, it's not b, is equal to c. This should be c. Okay, c equals 1 over 30. Okay. Now, if I substitute here, these are just constants, right? And I can write this thing, that y of t. So here we have, take this a out, that is minus 16 over 5. Take this b out, that is 25 over 6. Take this c out, it is 1 over 30. And what is the inverse Laplace transform of 1 over s minus 1? It is e to the power t. All right, here we have y of s is equal to this. And what is the inverse Laplace transform of 1 over s minus 2? It is e to the power 2t. Right? And how about this one? 1 over s plus 4. Our c is here. That is e to the power minus 4t. So that is the solution of the given initial value problem. And this is how we use Laplace transform to solve the differential equations, okay, of constant coefficients. Guys, any question? Okay. Strength does not come from what you can do. It comes from overcoming the things you once thought you couldn't. It's also a beautiful quote. Guys, that part is enough for now, okay? Let's have some break. After around 10 minutes, I will continue. We have one more session. It's about 20 minutes, okay? So at around 11:40, we will finish our class, okay? We will continue after 10 minutes.